Sure. Yeah. So today it's our pleasure to have Tuan Do as the first speaker of the BHI Colloquium Fall 2020. Tuan Do is an assistant professor in physics and astronomy department and deputy director of the Galactic Center group at UCLA. His research interest is mostly in understanding the formation of the galactic nuclei, the physics and astrophysics of supermassive black holes, and machine learning application in astronomy. And today we'll be talking about testing fundamental physics with orbits at the Galactic Center. So please, Tuan.
Great, thank you so much. I'm going to start sharing my screen now. Okay. Great, do you see the slides?
We do.
Okay, great. Thanks so much for the invitation. And I'm glad to talk to you about the work we've been doing at the Galactic Center. In particular, I want to focus on how we can use the Galactic Center to test fundamental physics. This work is done in conjunction with a lot of different folks. Here in the names of these folks are in the slides here. In particular, I'd like to highlight the many grad students who have been working on this project in yellow there. So to begin with, I'd like to talk about two questions today. One is general relativity the correct description for supermassive black holes? And two, are the fundamental constants of nature really constant? Now, why do we want to learn about general relativity? I really like the cartoon here on the right. So this is a cartoon of Einstein saying, we need to change space and time to make things work. And from off the screen, someone says, that's your solution to everything. I love this cartoon because this is literally true, right? If general relativity is true, it should apply to everything, both in space and time. But we know that actually our knowledge of physics is probably incomplete because our best models of physics right now, which is the standard model and general relativity, can't really explain a majority of the universe, actually. So we have dark matter being 24% of the matter of the universe, but there's no standard model particle that explains dark matter. There's dark energy as well, which is 71% of the energy density of the universe, which is very difficult to explain as well. So I think basically we need to be creative about testing some of our fundamental assumptions in physics in different regimes. And the Galactic Center kind of offers us a way of testing in a regime around a supermassive black hole. So this plot is a plot of the different tests of GR in different regions in this parameter space of, on the x-axis is the mass of the object where we're doing these tests, and then the y-axis is the gravitational potential. So you can see here from this plot that we have tests in the solar neighborhood down below here, and then the Galactic Center kind of falls over here in this region. And then of course, LIGO being mergers at the event horizon are all the way up here. So it's kind of important because we don't know what theories are going to be better at replacing some of things like GR to test these different regimes. In addition, some theories of gravity predict violations of GRs around black holes, but not around some non-compact objects like things in the solar system. So what is our test? So in 2018, the STAR SO2 went through closest approach around the supermassive black hole at the Galactic Center. And what we wanted to measure in 2018 was the gravitational redshift from the light coming from SO2. And so this video sort of tries to demonstrate that. At the very top is the radial velocity of the star, meaning that's the motion of the star away and, from us or towards us along the line of sight. And then the middle panel is the prediction that GR would have, the difference between the GR prediction versus the Keplerian prediction for the motion of the star. So basically, as the star gets really close to the black hole, the light from the star becomes slightly more red than we would expect using Newton's laws. And so this is the gravitational redshift. And the idea is that you should be able to measure this as it goes to closest approach. Okay. So as an observer, I'm going to talk about observations. This experiment actually required more than 2 decades of observing. And the reason is because in order to see deviation from general relativity, you need to know the Keplerian model extremely accurately so that you can attribute these deviations to general relativity and not just because of uncertainties in the orbital parameters. And so here is a video of the stars in orbit around the galactic center. So when you see dashed lines, that's when we've started tracking these stars with images. And when you see solid lines, that's when we started getting spectroscopy of the stars. So actually there's only one star in this region in which we've seen its whole entire orbit with both imaging and spectroscopy, meaning we have complete 3-dimensional information on this star for its entire orbit. So that's why this star is actually really important. And in 2018, there were actually 3 really important events to measure. You would think that, since the general relativistic effect is strongest at closest approach, we should concentrate on closest approach. But because there's a competition between the Keplerian components, knowing really well, and the general relativistic components, and these components are correlated at different points of the measurement. Actually, there are 3 really important points to measure. One is closest approach, but the other are actually the radial velocity maximum and the radial velocity minimum, which happened early. The radial velocity maximum happened for SO2 in April 2018, and the minimum happened in September. So, and a lot of this has to do with the geometry of SO2's orbit, actually. A lot of times it's actually really hard to visualize these orbits when you only see the 2-dimensional animation. So here is my attempt at making a slightly 3-dimensional plot to explain this. Basically, if I am the black hole and you're the observer, the star SO2 went in front of the black hole in April, basically. And then as it goes to closest approach, it went right in front, and then in September it went behind the black hole. So basically, there's a very small portion of SO2's orbit where it's in front of the black hole, and that's here denoted by these X's. And if you look at the cut along the plane of the sky, basically, that's when the star crosses the plane of the sky with respect to the distance from the black hole, which is why it makes these 2 points. These are the radial velocity maximum, minimum here, and it's why it makes them really important. Okay, so this is kind of our construction of the experimental design for this for these measurements. And what do we do to actually make the measurements? So we've historically been using the telescope on Mauna Kea to make measurements of the stars at UCLA. And in the front here, these are the 2 Keck telescopes. Actually, so in 2018, we used all 4 8 to 10 meter telescopes on Mauna Kea. And what you see are these lasers pointing at the galactic center. And these lasers are from the adaptive optics systems of these telescopes. So when you observe things from Earth, the atmosphere is actually a big problem because it causes lots of turbulence and it blurs all your images. And so what these laser guide star does is that it makes a fake star in the atmosphere at about 90 kilometers in the atmosphere using sodium light, the wavelength of sodium, which is why these lasers are orange. And then we basically track how this spot moves in the sky in the opposite way with the deformable mirror. That way you can take away the turbulence from the atmosphere. And all 4 telescopes now are equipped with laser guide star systems and can take these really precise or really high resolution spectroscopy in 2018. Okay, so going into 2018, we had this this big plan to the program to do this. And so I'm just going to show you kind of the bit of the progression of our observations in 2018, because I think it's a great way to introduce the team and the fact that this is a big effort. So in our first observations was in March. So in this picture, here's Andrea Ghez, who's been leading these observations since 1985. And then this is Anna Chula, who's a postdoc of the group. This is Devin Chu, who's a grad student. And what we didn't realize actually was how lucky we were to get this observation, because for the next few weeks, there were many, many snowstorms. So, these are things where despite the best planning, nature always throws you, can throw you a wrench. In fact, in 2018, Mauna Kea had historically bad weather for the last 10 years, basically. It has not lost so many nights as in 2018. So anyway, after several weeks of bad weather, we came back again and got some observations near the peak. So this is grad student Kelly Cosmo O'Neill, and this is a former grad student Sam Chappell here doing the observations. And then in May, there was a volcano. So the telescopes on Mauna Kea are located on Mauna Kea, which is a dormant volcano in Hawaii, but there's also an active volcano in Hawaii, which is called Kilauea. And here's what you're seeing exploding in this animation here. This happened right after we finished observing that morning, actually. So Mauna Kea has these great webcams where you can watch. And so as we were finishing observing, we're like, what is happening over there? So this is the explosion from the volcano, which is below the cloud level here. So the volcano caused a disruption in observing because sulfur from the volcano can combine with the water vapor on Mauna Kea to produce sulfuric acid, and that will destroy the mirrors. And so whenever the sulfuric levels were high, we basically couldn't observe. And the eruptions sort of went on and off throughout 2018. Anyway, we did get closest approach. Here's the team again at closest approach. And some of you may recognize also other faces here. This is Professor Mark Morris at UCLA. This is Joel Chen, who's a grad student at UCLA. This is Günther Witzel, who has now moved to Bonn to be a researcher. This is Arazu Degenfar, who's now a grad student at Geneva. Okay, and then as we go past closest approach, this is RV minimum. I think I've introduced Devin and Kelly. This is Abbalat, who's now a postdoc at UCLA, and this is Xiao Jia, who's a grad student at Berkeley. And this is near our final observations now in September. I think one new person is in this photo. This is Aurelian Hess, who's a theorist in GR and alternative theories of gravity. He stopped by to see what the fuss is about in terms of observing. Okay, well, so this is kind of like our slideshow of what happened in 2018 in the observing campaign. So now let's get to the nitty gritty, which is actually how do you put together all of this data, right? We have these data from actually 4 telescopes in 2018, but also 20 other years of data as well. And so I'm going to split up our discussion into 2 separate kinds of data types. One is the spectroscopy, which is what we're measuring along the line of sight. And in order to measure the spectroscopy of SO2 in 2018, this was really important because the redshift is a spectroscopic test, right? And so we used a physical model basically to fit the stars, and this physical model allows us to do things like fit the effective temperature of the star, the surface gravity, the metallicity, the rotational velocity, and the radial velocity. The radial velocity is the most important component, but it also lets us get to the physics of the stellar surface. So this software is called StarKit. It was built by Wolfgang Kurzendorf and I in 2015. This is an example of how it works. So this is an example spectrum of the star SO2. Now SO2 is a fairly massive star, and it's actually really hot in its atmosphere. So there are really only hydrogen and helium absorption lines in the near infrared where we're observing. So this dip here is from the absorption line of hydrogen at this wavelength, and this little smaller dip here is at a helium line here. So why do we go through all this effort? It turns out that by modeling it in a physical sense, we can eliminate a lot of systematics that we were having before. In the past, we just used a Gaussian model to fit the line because, I guess I should say that the radial velocity we're measuring is basically where the center of this line is compared to what the rest wavelength of the line is that we expect from Earth. And so that tells you the, that component. And so the centroid of the line is actually really important. So here's a test we did, which is in black, it's a star, a B-type star, which is similar to SO2. And then in blue is what a best fit Gaussian would look like. And in orange is what this physical model looks like. You can see that the physical model fits much better the shape of the line and also these little shoulders. And indeed, we found that using standard stars that our previous method had a small bias in the rate of velocity of about 8 kilometers per second. And that by using this new method, we've eliminated that bias. The other nice thing about using a physical model is that we can improve the precision by a factor of about 1.7 because the shape of the lines are dictated by physics rather than your Gaussian fit. Okay, so what does the data actually look like? Here's just a gallery of the data. So on the left here is if you combine all the data ever of SO2, you can see like these little tiny lines like helium here, this is a helium, this is a hydrogen line. But if you, and then in this panel, I show spectra from 2017 to end of 2018. So basically, right, you can see that the SO2 moved from, positive almost 4,000 kilometers here in March and April to minus 1,600 kilometers. So in 1 year, its velocity changed by 6,000 kilometers per second. So this is a very fast moving star. And that's why it's experiencing all these relativistic effects. So the other important component is the astrometry, meaning the measurement of the position of the stars in the images over time. And this is a nice animation done by Amama Gautam at UCLA of all of our images. So this is fairly minimally processed. We just sort of align all the images so things are stationary. So you can see how the stars move over time from 1995 to 2018, basically. And so in this video, the circle is the star SO2. That's the one we're tracking. But you can see how all the other stars are moving too, right? The other interesting thing that you may notice in this video is Sagittarius star. If you look at the spot, you'll see that if you can see it flicker over time. And so that's the near infrared emission from the black hole, actually. The other thing about this image is you can see at earlier times, it looks poorer quality than later times. And that's because in earlier times, we used a technique called spectral imaging, which didn't use adaptive optics. And in the later times, we had adaptive optics, which went much deeper. So in terms of the astrometry, there are a few improvements we made for this experiment. One was that, like I said, those early images from 1995 to 2005 use this technique called spectral imaging, which is just where you take very, very short exposure images of the atmosphere, basically below the, shorter than the time which the atmosphere can change. So typically like 1/10 of a second. And you take thousands of these images. And then at the end, you shift these images and you stack them together to make a deeper image. So this helps you preserve the angular resolution, even though you don't have adaptive optics, but it's not very deep in terms of detecting stars that are faint. It's also depends on the algorithm used to combine it. Anyway, so like over in the 20 years since the first observations, our computational algorithms are much better. And so we've been able to get re-analyze these images. The other thing we've been doing is to get better optical distortion maps. So basically, you want to be able to characterize how optical distortion, say in the lenses or the detector of the telescope, changes your positions. We also have better alignment methodologies between different epochs. And then lastly, we use a bluer wavelength to do the observations in 2018 than in past. And that's because the emissive source from Sagittarius star, the black hole, actually it's really red. And when it becomes bright, it can actually interfere with your positional measurements. And so by going to a bluer wavelength, you reduce the amount of bias that Sagittarius star has. The other thing that always plagues us at the Galactic Center is stellar confusion, meaning you can have stars that cross each other all the time in projection because there's just so many stars. This is an illustration of that. You can see that on the left, stars at the Galactic Center, and then in in orange circles are the positions of all the stars that we've detected in this map. And one thing you can do is subtract all the known sources, and then you can see all the sources that you might have missed. So for example, this is SO2, and you subtract all the sources, you can see that there's actually a source that crossed SO2 here in 2014. Anyway, it required a lot of data for us to see that some of these epochs were anomalous in the past, and then to try to dig down physically to figure out why it was happening and to correct for this in terms of the astrometry of the orbit. Now I'm going to move into this question, which is maybe deceptively simple, which is if all stars move, how do you put them on a common coordinate system? And this is a question of reference frames. So if you ever want to give anybody who does astrometry a hard time, ask them this question, like how did they build the reference frame? It's often the largest source of systematic error for astrometry. In the Galactic Center, as you saw in that video, like literally all the stars are moving. So how do you pin everything down? And it would be great if we can say observe something in extragalactic source that doesn't move. So say like quasars, which are far away, so they shouldn't move. But unfortunately, we don't see any of those. And so we do the next best thing, which is we bootstrap off of radio masers. So radio masers are stars in which are actually quite bright in radio wavelengths. And at the radio wavelengths, the Galactic Center is much more transparent. And so folks can use to measure the radio observations of these masers and quasars further. That's extragalactic, so that in the radio you can find the absolute coordinate system to place all these stars in. And so in the infrared we can see these stars as well. And so we use these stars to basically build our reference frame. Okay. The reference frame stability is super important for getting a stable orbit. I'll talk to you exactly why, but in 2019, we were able to improve our reference frame method by about a factor of 4. And the way we test the reference frame is that you can see how stable the reference frame is. So basically you can see how fast the reference frame is drifting as a function of right ascension and declination in the sky. So in 2018, it's basically much more, our uncertainties are much smaller. You can also see how well the reference frame is centered on Sagittarius star, which is the black hole. Presumably, since we're measuring the orbits around the black hole should not be drifting with respect to the stars. Okay. What you can see from reference frame stability actually is in the orbits themselves, right? So if we think that the black holes should not be, when the reference frame is not stable, what happens is that it looks like there's a precession in the orbit, essentially. Basically, the orbits don't close. And this is what you see here, right? So when you go all the way around, you see that the stars don't connect. And that's because your reference frame is slowly drifting in another direction. So by fixing this, you can you have much more accurate control of this drift. And this will be important later on for, say, measuring the precession of the orbit. We also included a number of systematic uncertainties. We also examined a number of other systematics, but I won't go over them for time right now. So what happened? Like basically when you put it all together, what do you get? So we parameterized the relativistic redshift as a scale parameter in our fit. So here's the equation, roughly the equation we use. This is the observed radial velocity that we see. We break up this fit for the radial velocity into these components. The first component is just a radial velocity offset. So basically the Sagittarius star plus SO2 system can be moving away or towards you. Then there's a radial velocity from the Keplerian model. So that's how fast the orbit is moving, just due to Newtonian gravity. And then there's these two relativistic components. There's special relativity, which we assume to be true. And then there's a general relativistic term. This is the gravitational redshift, essentially. And it's parameterized by this parameter, the redshift parameter. So if this parameter is 1, then that's GR. If this parameter is 0, then that's Newtonian. So essentially, we're trying to constrain this parameter. Okay, so this is what our orbit looks like. This is on the left is the points on the plane of the sky. So once again, this is the line of nodes, meaning this portion of the orbit is in front of the black hole and this whole portion is behind the black hole. This is the radial velocity measurements. In black are the new measurements here, and this is the residuals from the fit. Okay, so one of the first things you could do is to do a hypothesis test, basically, of Newtonian model for the orbit versus general relativistic model. So we do this by doing something called Bayes factor, which is basically the ratio of the probability of observing your data given the GR model compared to the probability of observing data given the Newtonian model. And the Bayes factor here is about 10.7. So what does that mean, though? That means basically that the general relativistic model is about 43,000 times more likely than the Newtonian model in explaining the observations. So we're definitely seeing non-Newtonian effects. And then you can test GR itself to say now, okay, instead of saying it's a GR model better, what is the measurement of this redshift parameter? So when we look at this is in this dash to look at this deviation from Keplerian, from Newtonian, basically. So like I was showing earlier on in the animation, general relativity predicts there to be this kind of spike in the redshift in 2018. So if Newton is correct, then you would see nothing, which is 0 down here. And our model uncertainties are these shaded regions. And so our posterior distribution for the best fit is about 0.88 plus or minus 0.17. So it's consistent with GR, which is 1 at about the 1 sigma level. Okay, well, what does this tell us about the nature of gravity around supermassive black holes? I would say Einstein appears right, as many of these tests have shown, for now, I think. But I think it really is opening up a way of testing general relativity at the Galactic Center and in more stringent ways that we can do in the future as well. What else do we get from these orbits? The other things we can get from the orbit, of course, is the mass of the black hole and the distance to the galactic center. Now, these measurements have gotten very, very precise. They're below 0.5% precision now, I think. And so the black hole, it's about 3.95 times 10⁶ million solar masses. And then the distance to the galactic center is about 7,900 parsecs away from Earth. You can also look at how much mass that's not in the black hole inside of SO2's orbit. So we call this the extended mass. So to do this, we assume that GR is correct and then ask how much extra mass there could be in the SO2 orbit. And at 68% confidence interval, we think there's less than 5,000 solar masses of material. And very briefly, the next test that we'd like to do would be the precession of the orbit of SO2. So the precession is, it's another general relativistic effect, which we see in the solar system, for example, in Mercury. So basically, the orbit of Mercury doesn't come back to where it starts. And this should happen for SO2 as well. And recently, observations from gravity interferometer showed precession in this orbit. So on the left here are the figures from the gravity team. This is the best fit orbit now for SO2, and then they've parameterized the precession signal as well to be this parameter f, where it's 1 if it's GR. And they find that there is agreement with general relativity. So in order to get this precision, there were some, their analysis included new data from 2019. They've included additional priors in the reference frame. Like I was talking about before, the reference frame can drive a lot of the changes in the orbit. And so fixing these reference frame parameters are very important. And the way you fix these parameters can affect your results. I think they've also fixed the gravitational redshift and assumed no extended mass for this analysis. So I don't have any new reports on this aspect from the data from Keck, but I'll just give you a little bit of preview of like some of the things we're thinking about. And one of the things is that we're finding it kind of difficult to disentangle the effect of GR from extended mass. And what I mean by this is that the general relativity causes the orbits to precess in one direction, but if you have mass, extended mass, it causes the orbit to precess the opposite direction. So this is purely a Newtonian effect. And so if you include both components into your fit, the precision that you can measure either of these drops a lot because you have this degeneracy. And one way of resolving this degeneracy is actually using multiple stars, because if you use other stars, which are further out, they should not feel the same general relativistic precession as SO2, but they should feel the extended mass. And so you can use these to decouple them. Okay, so stay tuned for more about this. But I'd like to move on to my second topic, which is, are the fundamental constants of nature really constant? So I think this topic it's really interesting to study because of a few reasons. One is that local positional invariance, which I was showing with the cartoon earlier, basically is that the laws of nature should be the same everywhere, right, in space and time. This means that fundamental constants like the speed of light, say, or the charge of an electron should be the same if you're near a black hole or on Earth. The second is that a lot of the other theories of physics beyond general relativity or the standard model indicate there may be variations in the fundamental constants. So for example, unification theories, quantum gravity, and some models of dark matter and dark energy violate this equivalence principle. The other is more philosophical, which is the anthropic principle. The reason we're here is because the values of the constants are the way they are, but we don't have any a priori reason why these constants are the numbers they are in the theories that we have today. So if we're able to find variations in these constants, it may point at a more fundamental theory that might help us explain why these numbers are the way they are. And there's a particular constant called the fine structure constant, which is really ideal candidate for these kinds of tests. And the reason is because the fine structure constant governs the electromagnetic interaction. And so it governs the physical processes such as atomic transitions. So here's its definition. The fine structure constant is actually composed of several other constants, including the electron, charge of electron, over Planck's constant, and the speed of light. It's dimensionless. It has a unit of about it has a value of 1 over 137. And the nice thing about the fine structure constant is we can test its variation using atomic line transitions. So using spectroscopy, which we can do at lots of different cosmic scales, essentially, both on Earth and then much further away. And very intriguingly, astrophysical tests with quasars and white dwarfs have found signs of variations in the fine structure constant. So how does these tests work? So quasars are basically black holes that are in the very distant past, and they're very bright, and so they can be seen far in past, and between the quasar and us, there usually are these clouds of just gas, basically in the middle, and these clouds are at different distances from the quasar and us. And because the light from the quasar passes through these clouds, we can see absorption lines from all the metals and atoms in the clouds. So you can use these absorption lines to test for variations in the fine structure constant. And in fact, there have been reported significant variations. So for example, here Webb et al. Reported about minus 0.74 plus or minus 0.17 times 10 to the minus 5 for quasars that are further than a redshift of 1.8 or so. There is some controversy here, though, because some other works have looked at different samples of quasars and don't see this variation. In a different regime is white dwarfs. So white dwarfs are basically the remnants of stars like the sun. After they die, there's a very compact core. And the surfaces of white dwarfs have very, very strong gravity compared to the Earth. And so you can use the surface of white dwarfs to look at how fine structure constant might change with strong gravity. And actually, very recently, as of like last month, actually, there was a report from on arXiv which showed that on one of these white dwarfs that there might be a 3 sigma or so detection of a variation in the fine structure constant. Okay, so that basically, I think, is very good motivation for trying to look for variations of fine structure constant around a supermassive black hole. Now, this is a very different target than quasars and white dwarfs, and it has a totally different set of systematics as well. So how does our experiment work? So what we are looking at is we're looking at different stars at different distances from the black hole. And so you can measure the variations in the fine structure constant then as a function of gravitational potential this way. How do these measurements work? So but basically what we're doing is trying to measure the positions of stellar lines very precisely and then compare the relative spacings from the star near the black hole compared to the Earth, right? So if the fine structure constant is the same, the relative spacings of these spectral lines should remain constant. And so this is composed, this separation between what you see at the Galactic Center and what is in the lab is this delta lambda over lambda. It has these two components. One is that the star has some motion, right? So it's this is the redshift I was talking about. So it's moving away or towards you. And then it has this component, which depends on the fine structure constant variation. And then kappa or K, this is the, this has to do with atomic physics of that line, essentially. And that's, that can be calculated and tested in the lab. So if you have many lines, basically, you can fit for these two red values. It turns out that the stars I was talking about earlier, SO2, is not a good star to use for this test. And the reason is because it doesn't have enough lines. And in fact, when we use late type lines, so these are red giants at the Galactic Center. And because they're red giants, their atmospheres are very cool, which means that you can start seeing metal absorption lines. The electrons in the metals have not all ionized, basically. And so this is an example of a spectrum of a star at the Galactic Center. You can see these very strong metallic lines here. And this is what we use. The other advantage actually is that metal lines are between 10 to the 4 to 10 to 5 times more sensitive to variations in the fine structure constant than hydrogen and helium, which is what we see with SO2. And so very recently, we've performed the first limits on the fine structure constant variation around a black hole. This is kind of the same diagram previously as with the GR test, but with fine structure constant tests, basically. This is the mass of the object you're doing a test around. This is the gravitational potential. This is kind of the range of the S stars where they lie compared to white dwarfs. And then you can also see how compact the object you're doing a test in. So we're working on a supermassive black hole, which is very compact. So in the end, we don't yet find a significant variation in the fine structure constant at the level of about 6 times 10 to the minus 6 or so at the Galactic Center. So to give you a comparison, this precision is about 4 times worse than the quasars right now, and about 2 times worse than the white dwarf precision right now. But in the next couple of years, with new observations and more more spectral lines, I think we can get, we improve this by a factor of 10 to 100, basically. And so I will just end with some thoughts about GR. So it's a really exciting time, actually, for this work. Oh, sorry, somehow my PowerPoint crashed. 1 second.
We're glad that it happened at the end.
Yeah. Okay. Okay, so it's basically just it's an animation I made of the of what we're doing today, which is here with adaptive optics today. And then in 2 or 3 years, this is using the new upgraded AO system at Keck, and then with TMT. So I think we're just starting to enter into the world of these fundamental physics tests, and we're just going to get much better in the future. So for example, with TMT, we expect to see stars with orbitable periods about 3 years. And so a lot of these effects will now become like possible for like a grad student career to look at. Okay, and then these are the related papers. There's a huge number of people who worked on this, and a lot of related work. And I'll just end with 2 things, which is we've entered an era of fundamental physics tests with stellar orbits at the Galactic Center, and understanding systematics will be crucial as we move forward. So yeah, thank you very much. Take any questions.
Thank you, Tuan, for this very, very interesting talk. So we have about 15 approximately minutes for questions.
Yeah, so
Go ahead,
if I may ask, is there any way you hope to learn about the spin of the black hole from the orbits?
That's a good question. I think it's going to require more precise orbits. The effective spin is very small. So potentially, if you want to do it directly with the orbits, will probably require maybe a decade of observations with TMT to get the astrometric precision that you need.
So we actually got a question that is related to this one from the public. I was wondering if you're interested in answering this. So someone asked if you're able to measure also the precessions of the node and the inclination, because they are affected by the black hole spin.
Yeah, like I said, like eventually it will become possible, but right now that effect, like the spin effect on those, is too small to be detectable. Okay, so there is Gary who has a question.
Yes, hi,
Yeah.
This is Gary Melnick. A question going back to your stellar model fitting of the absorption lines. In particular, at closest approach, where the most physics is extracted, is there enough tidal disruption of the star that the stellar models that you're using have to be modified in some way? I mean, I presume you're using a model that is sort of a steady state model for the star of that spectral type. Is that good to the precision necessary in the presence of the very strong gravity at closest approach?
So the short answer is, I think yes. So the star passes at a distance of about 100 AU from the black hole, and given its mass, it shouldn't be, like tidally affected very much. But on the other hand, what's nice about this model is that we actually let all these components free. So So we can see if, say, like the radius of the star increased, or if the temperature of the star changed as it goes through closest approach, because we fit every single night separately. And right now, when we look at these parameters, they're consistent between like closest approach to further away. So we don't see any physical changes to the star.
Thank you.
Avi, you have another question? You still have the hand raised. No. I actually have a question for you. You were talking about the extended mass at some point around the black hole, and you mentioned that it's like 3,000 or 5,000 solar masses. So I imagine this is both other stars maybe inside and the accretion disk. So I'm not sure that I fully understood how you are discriminating between the mass of the black hole and the extended mass around it with GR.
Right. So that was kind of one of my points, which is that to do that extended mass calculation, we had to assume GR was correct. So we fixed GR, and then we asked how much basically precession does the orbit have, right, due to just the Newtonian component of an extended mass distribution. So we assume an extended mass density profile, and then fit for the total mass enclosed in SO2 due to this extra component. If you add extended mass into a model where you also fit GR, it makes there to be too many free parameters to have strong constraints on either, essentially.
Okay, thank you. Any other question? Well, if not, I guess we end up here. Right, Avi? You have something to add?
No, I just wanted to thank Tuan for an excellent talk, and it was very informative and interesting. We haven't heard these details before. Thank you.
Great. Yeah, thank you for the invitation, and hopefully we can meet in person one day.
Yes.
Would be great.
Okay, so thank you everyone for joining us, and we'll see you again a week from now. Bye-bye. Take care.